And we're back. The last video for AP Calculus AP sample test number 2. Multiple choice numbers 38 through 45. Again, we are allowed to use a calculator for all of these problems. We don't have to, but we are allowed to. So let's start with this one. Consider the function sine of x over x k. It's a piecewise function. The reason it's piecewise function is because you can't plug in 0. What this is really asking us is, what is this approaching near 0? What's the limit of that as it is approaching 0? And if we could fill that hole in, then could we make it be continuous at x equals 0? Well, that's saying what's the limit of, as x approaches 0, of sine of x over x? Hopefully, you guys remember this. But let's say that we wanted to check it just in case. This is a special trig limit, but if I wanted to visualize it just to see it, I can help you guys see it a little bit here. It's actually part of the squeeze theorem to really look at it. But let's see what we got. Sine of x divided by x. So we want to visualize that really close to 0. So I'm going to go from negative 0.01 to 0.01 in my x values. And I'm going to be bouncing back and forth between negative 1 and 1. So this is kind of hard to see, but if you look at that, we almost need to zoom in even closer. So let's see what we can get. So we're going to go from negative 0.1 down to 0.1. Let's make sure that we typed in our graph correctly. Sine of x, then divided by x. So it's kind of hard to see what's going on here. It looks like it's getting really close to a value, but even then, do we really know what that equals? One way that we can check it, we're going to go ahead and put here the limit of as x approaches 0 of sine of x over x is actually equal to 1. The other special trig limit that you guys should have remembered is the limit as x approaches 0 of cosine of x minus 1 over x. I think it might be 1 minus cosine of x, but anyways, that's equal to 0. So here we go. The answer would be 1. That's just memorizing this. There's not a lot we need to memorize in calculus, but that's one of the things. Okay, in the interval from 0 to 5, the graphs y equals cosine 2x and y equals sine 3x intersect 4 times. So, and it's saying that these times are a, b, c, d, and 5. A, B, C, and D. Which of the definite integrals represents the largest number? Well, let's see if we can visualize this graph to help ourselves first. So if we're looking at these two graphs, one is cosine of 2x, cosine of 2x. And the other one is sine of 3x. So let's see what this graph looks like. Oh, we know where we need our window. We're going from 0 to 5. So we're going to start at 0, go up to 5. And for our y-axis, we really need to be between negative 1 and 1. How do I know that? Because we have sine and cosine graphs. They're just waves, and they have an amplitude negative 1 and 1. You know what? There we go. I have a feeling that we might be in a different mode. Let's double check that. We are, and that's what was happening in that last problem as well. I was wondering why I was coming out with something different. We need to be in radians. Here we go. Much smoother curves. Okay, so we intersect here. Now we need to figure out which one's on top and which one's on bottom. Well, from A to B, here. So let's look at from A to B, then from B to C, and then from C to D. We have 3 different regions that we're looking at in there. We also have from 0 to A as well. Well, from 0 to A, cosines on top, sines on bottom. So from 0 to A, it's cosine on top, and then we got the sine on the bottom. And then from the next region, we're looking at sine being on top and cosine being on bottom. So now we're going to have sine on top and cosine on bottom. And then for the next one, we have it actually, let's see, do we switch here? We have sine, no, it stays the same. So this one's going to be still sine on top, cosine on bottom. Then for the last one, it should switch, but just to double check. Yes, we have our cosine graph that's coming down here a little bit longer period, and cosine is on top and the sine is on bottom. So if we're looking from 0 to A of cosine 2x minus sine 3x, that's at least positive, but it's not very big. When you look at it, it's a pretty small area in here, so that's probably not going to be the one that we're looking for. If we're looking from A to B of sine of x minus cosine of 3x, or cosine of 2x, or from B to C, these two look the same. Well, let's take a look at that real quick. They do look the same. They're very symmetrical here, if you notice. They're almost so close to being the same that I doubt that either of those would be the correct answer. From C to D, and we're looking at cosine over sine. We want to make sure that the cosine one's on top, the sine one's on bottom. If they're flipped, like they are here in part E, that would make the answer or the area negative. It's a negative value. So that means the answer we're really looking for is D. We're going from C to D, so from this point to this point here. And it's got a much bigger area than any of the other 3. So that would be our answer. It's just interpreting the graph, really. You don't really have to do much other than graph it, know which one's on top and which one's on bottom, and then see how the area would be calculated from that. The function f of x equals tangent of 3 to the x has 1, 0 in the interval 0 to 1.4. The derivative at this point. So we got to first figure out where is the 0. Then calculate the derivative at that point. That's easy enough. Let's go ahead and graph it. We got tangent of 3 to the x on the interval 0 to 1.4. So go back to my y equals. I'll clear these. We have tangent of 3 to the x. And our window is from 0 to 1.4. Let's see what our graph is. So there's our 0 right there. How can I figure out where that is? Well, I can use my calculation function. So if I do second calculate the 0 to, I know that I can get kind of close here. I know it's at about 1. So that's the left side. Then if I go to the right interval, I know it's somewhere between those 2 points. And the actual value that it's at is x equals 1.04. 1.0419 if we want to go out a little bit further. 1.0419. So we know that x equals this. We want to find f prime of 1.0419. And notice that they actually have that as one of the values. That's probably not what the actual slope is. It's probably a distractor. We have to find the derivative at this point. To calculate the derivative, well, that's another function here. We do second calculate. Now the derivative is here, 6. We're at 1.042. That's pretty close, but I'm going to go ahead and type in the value here, 1.042. 0.0419. And our derivative is about 3.45. Well, that's C. That was easy enough. That's just a calculator function. Do you know how to use your calculator well? 41. Now, this one's not too hard, but if you're thinking about it, is a lot of calculations. It's fewer calculations than you would think. We have this integral 0 to 6. It's being approximated by Riemann sums. Notice first that we have 3 intervals of width 2. So that means I'm going to have 3 boxes, each with a width of 2. Now I need to figure out what their height is. To figure out what their height is, I need to determine am I doing a left, middle, or right type rule. This says I'm going to use the midpoint. Well, if here's my first box from 0 to 2, then my second box is going to go from 2 to 4. Then my third box is from 4 to 6. That means I'm going to be using the midpoint as the height for each of those 3 boxes. So the first box has a height of 0.25. So the height here is 0.25 and the width is 2. Then for the second one, I'm using the midpoint, which again is at 3. The height is 0.68 and the width is 2. Then for the third one, I'm using the midpoint for the height. So the height is going to be 0.95 and the width is 2. So all I really need to do is calculate these areas, add them up. So I have 2 times 0.25 plus 2 times 0.68 plus 2 times 0.95. I notice that I can factor out the 2 and just add those together. 0.25 plus 0.68 plus 0.95. Let's go ahead and do the calculator now. We have this 2 times, and then in parentheses 0.25 plus 0.68 plus 0.95. Come out with 3.76, so our answer is right here, 3.76. 4 more to go. We are very close here. Ooh, this is interesting. We have a derivative and an integral in the same connection. What happens when you have a derivative of an integral? Well, that's fundamental theorem of calculus. It's fundamental. It's the second part, if you were to really think about it. It's really fundamental theorem of calculus part 2, if you were to try to research it. But it basically says that the derivative of an integral from a to b of, let's say, some function of t dt, doesn't really matter what this is, it just shouldn't use x, just to keep it not so confusing. That equals f of b times b prime minus f of a times a prime, meaning that the derivative undoes the integral, but then we have a chain rule that happened because b and a could be functions just like they are here, x cubed and x. So when they were plugged in, they have a residual derivative that doesn't get canceled out. In fact, that doesn't get canceled out by the integral, it sticks here. So we have b and b primed. So I need to have, if we have sine of t squared, that's going to be sine of x cubed squared times the derivative of x cubed, which is 3x squared, minus sine of whatever that other one squared, what's the other one, x, times the derivative of x, which is 1. Well, sine of x cubed squared is going to be sine of x to the 6th. And this 3x squared, we can move that out front. We're going to subtract sine of x squared. Let's see if that matches anything that we got here. It sure does. C is our answer again. Number 43, a tank is being filled with water at a rate of, oh wow, we got a measurement at a rate. And a tank is being filled. I wonder what kind of tank this is. Well, it doesn't actually say what kind of tank it is. It should, even though it doesn't. But let's see what happens. We first know that the rate of change of the volume is changing in terms of time. So it's 300 times the square root of t. And t is greater than 0. If the tank is originally empty, how many gallons of water are in the tank after 4 hours? That means that the original when t equals 0, the volume equals 0. And if it's asking us how many gallons are being filled here after 4 hours, that's an accumulation problem. It's saying how much is accumulating over 4 hours. Another way to think of accumulation is integration. So that's the integration from time equals 0 to time equals 4 of 300 times the square root of t, dt, of course. Now I could do this by hand, but you know what? This is the calculator section. Let's make our lives easy. So first thing I need to do is plug in the function here. I have 300, and x is going to be our variable of integration, just because it's a little bit easier. We have second, where's square root at? Square root of x. So we're going to integrate that. I need to plot this from 0 to 4, so let's go ahead and do that. Make sure my window has 0 to 4. I have 0. I need at least 4 in there. I'll go all the way to 5 if I need to. Go to the graph. Now the graph is actually off the page. I don't really care about that. What I do care about is calculating the area. So let's go ahead and second and calculate the area, which is number 7 down here. Calculate 7. My left bound is 4. My lower limit is 4. Press enter. My upper limit is going to be, whoops, my lower limit was 0. I actually did say that. And my upper limit is 4. It's going to shade in the area, which is way above the screen, way out of our view. But it gives us the value down here, 1600. The answer is D. Calculators are awesome when you know how to use them. How many gallons after 4 hours? 1600 gallons. 44. The region in the first quadrant enclosed by the graphs y equals x, y equals 2 sine of x is revolved around the x-axis. The volume of the solid generated is, wow. See how each of these are not even in terms of pi? That means we're definitely going to have to use our calculator for this. Let's go and see what we got. So we're going to go back to y equals. We're going to take away this function. We're going to put in x for one function and 2 sine x for the other one. 2 sine of x. Let's graph that. Well, our function kind of goes off the page. We're really looking at, what's the area between these curves. It's going to be up here, and we need to go at least as high as 1, but probably even a little bit higher, probably up to 2. So let's do that real quick. Let's set our y maximum to 2. Now let's try graphing it. There we go. So this region right here is the piece that we're looking at. The curve is the sine. Pardon me. The bottom is the linear function. So, and we're revolving around the x-axis. So I'm going to redraw this on our graph here, just to give us kind of an idea of what we're looking at. So we have the curve, the sine curve. Looks kind of like, whoops. That. Then we got the other curve, or the straight line, looks kind of like this. And the area that we're trying to find, the region, is this blue stuff here in the middle. So what we want to do is revolve this around the x-axis. So then what we're really looking at is how are we going to figure out the area of those disks? Well, there's a couple of questions that we need to ask. This is our axis of rotation, and when you're doing a volume of rotation, you want to say, am I attached or empty to the axis of rotation? Well, we are empty. We have lots and lots of green space here in the middle. That means that we have to follow a template where we do pi times big R squared minus little r squared. And we're going from A to B, or left to right. Well, here's A. A is 0. But then we got to figure out, what's B? Well, we don't know what B is. So let's go ahead and figure that out on our graph here. If we try to find the intersection, that's just going to be second, calculate, and it's the intersect, 5. it looks like it's at about 1.7. So on the first curve, I'm going to say 1.7. Ooh, looks like we got to actually scroll on it. Second, calculate the intersect. So first curve, you need to be around 1.7. We're too far to the left, so we're about here. Second curve at about the same spot. Guess right about there, looks good. The intersection is at x equals 1.8954. So x equals 1.8954. So for B, x equals that. Now we just got to figure out our big R and little r. Let's do them color-coded. So big R I'll do in blue, and little r I'll do in red. Big R is always from the axis of rotation to the outer edge. So that's all the way here. So that's going to be sine of 2x, or 2 sine of x, pardon me. 2 sine of x minus 0. And we're going to have that as our big R. And our little r then is going to be this inside piece. And little r is equal to just x. So if we're trying to find this integral then, if we're to simplify that, the volume is equal to pi times the integral from 0 to 1.8954 approximately. We should say this is the approximate volume. Times r squared, which is going to be 2 sine of x quantity squared, minus, then little r squared is just x squared. X squared. So let's go ahead and type that in as a full function. So I'm going to turn off the first and second functions here on the graph, just so we don't get confused. But I'm going to use them because those represent my big R and little r. So to use them, I can go to vars, then y vars, function, and y1. So we got y1 squared. Actually, I want to go in front of that now. We want to insert another one. So I'm going to go to y vars, function, and we want y2 for the other one. y2, and we're still inserting squared, and then a minus. So this represents big R squared minus little r squared. You might be asking, well, you need a pi in there. Sure, we could put a pi in here. That's fine. So we're just going to insert seconds. Insert pi, which would be this value up here. We still have the insert part, so we're going to open the parentheses and then close it off here. So that's what we're actually trying to integrate. So let's see what the graph of that looks like first. It's kind of up and down. We're really going to be probably looking at this area in the middle here. So that's going to be from 0 to 1.8954. So that means we need to integrate. Second, calc. We're going to integrate, which is number 7. We're going to start at 0 for our left bound. Our upper limit is 1.8954. And our area is equal to 6.677777, or D, 6.678. Last question of the night. If y equals this, then the nth derivative, that's saying f to the nth derivative of x. Ooh, this is going to be a little tricky. First we got to see what happens in the derivative. So let's look at just the first derivative, y prime, or dy dx, the first derivative. Well, it's a product rule. Let's say x is our u and e to the x is our v. It's always going to be u prime v plus v prime u. X primed, or the derivative of x, is just 1 times e to the x, is just e to the x. Then v primed is e to the x. Well, that's simple enough so far. Plus, or times u, which is just x. Now notice that we have our original function in our derivative here. So y double prime is just going to expand on that. The derivative of the first term is just e to the x. The derivative of this second term, x times e to the x here, is the same thing as the whole first derivative. So we're going to do plus x e to the x, or let's rewrite that real quick. So it's going to be plus e to the x plus e to the x times x. Now if we do y triple prime, that's going to be e to the x plus e to the x, because the derivative of those is just straightforward, same thing, nothing changes. But then we have this thing here that keeps getting added on, plus another third e to the x plus e to the x times x. So it's growing. So if I were to look at this, I could factor out e to the x from all of these here. That would be e to the x, and I got 1, 2, 3 of them, plus x. So the y to the third derivative is e to the x times 3 plus x. So if I were to follow that pattern, I could assume that y to the nth derivative means this 3 is now going to become just n. We have an x, and it's times e to the x. The only thing that looks like it would fit that pattern is C. There's your answer, and the multiple choice is done. Tomorrow night we will have the FRQs available.